So let's go through a PID controller example, and this example is of course a very simplified version of the true world. But we have a cruise control in a car, and the power given to the wheels is on a linear scale here. You have 7, which means the pedal to the floor, and you have -3, which means that the pedal is lifted all up, and then you actually do a braking, an engine braking. So let's say that we have the cruise control. It's adjusted to 60 kilometers per hour. The real velocity is 55 kilometers per hour, and we are running on an infinitely long upward hill, so the velocity is falling. And since the cruise control was turned on, we should ideally have reached 5 kilometers by now at 60 kilometers per hour, but we have only reached 4.7 kilometers, so we are actually a bit behind the desired distance. So let's see. The P controller senses that there is a difference between real and desired speed, which is 5 kilometers per hour, because the job of the cruise controller is to decide what speed, what velocity we should have. And the P controller detects this, that the real velocity is 55, the set value is 60, so there's a deviation here of 5 kilometers per hour. The P controller doesn't sense that the same acting power has been used for a long time without having reached the desired value, so that would be the steady state error. We have, since we here, we are actually 300 meters behind the desired distance. That would mean that we, since we started, we have actually been running too slow. But that is not detected by the P control, because the P control only looks at the current deviation or error. It doesn't sense that we are actually losing velocity since we're going on an upwards hill, because it's only looking at the current difference between the desired and the true value. The I controller doesn't sense that the velocity is too low. The integral only looks at the covered distance, because the integral of velocity is distance. So the I controller will act based on that we have reached 4.7 kilometers while we should have been at 5 kilometers, that we are at 300 meters behind the desired value. It doesn't sense that we have negative acceleration. So the P controller would suggest an acting power of 3, the I controller an acting power of 2, and the D controller is the one that senses that the acceleration is negative and will suggest an acting power of 1 maybe. The numbers here, of course, are based on how much each of these parts here should count in the total here. So the sum of suggested acting power is 6, which means rather hard step on the pedal here. So let's go to the moment where we are entering flat landscape. The upward hill has now become flat landscape, but the real and ideal velocity difference is still 5 kilometers per hour. So it still suggests the acting power of 3. The I still notices that we are for 300 meters behind the ideal distance and still suggests the power 2, while the D control is the one that immediately discovers that we are starting to accelerate. So it would suggest an acting power of -1, because we're now accelerating, and the D controller would actually like us to have no acceleration, not negative, not positive. So the sum here is 3 plus 2 minus 1 is 4. So here is the suggestion when we just went from upward hill to flat. We are getting close to the ideal speed. The P controller notices that and suggest an acting power of 0 because we now have 60 kilometers per hour. And the covered distance still 300 meters behind, so the conclusion would be 2. And we are accelerating -1, so the sum of acting power is now 1. Conclusions. The Pid controller on its own will never give the ideal speed, since it will recommend less and less acting power as we are getting closer to the ideal speed. At some point, the acting power is equal to the loss to aerodynamics, friction, rolling friction, etc. So we need to have some power in order to maintain the speed, but the Pid controller doesn't look at that. The Pid controller only says, okay, we have the same speed as the desired speed, 0 power. However, this is the only controller who knows when the ideal speed is reached. The eye controller on its own will recommend that we drive too fast until the ideal distance is reached, but then the acceleration is so high and the velocity also is so high that we will overshoot, which will lead us to braking, and then a new acceleration, new braking, and the eternal oscillations will then occur. However, this is the control that will help correcting the steady state error from the P here. The D controller on its own will recommend 0 acting power at 0 speed. Remember, no acceleration, no power. It will also recommend 0 acting power if we have a constant speed of 100 km per hour. However, it will quickly sense a new uphill or downhill slope and recommend acting power immediately. So this is the one that speeds up the system. This flow chart is quite important. Which controller should you select? You have actually 3 options. You have P control alone, you have PI control, and PID. You never use PD, so you have P, PI, or PID. Do you accept a steady state error? If you do that, you can use P control alone, which would actually mean that you set the integral part and the derivative part to 0. But if you can't accept the steady state error, you have to go further down, and then you ask yourself, do we have noise in our measured signal? If we have that, you can forget using the derivative part because that would amplify the noise. So then you have to use PI control. If you don't have noise, you can go for this final question. Do we need a more damped response? The damped response is that it damps the overshoot and undershoot, and that would mean PID control. If you don't require more damped response, drop the derivative part because of the noise sensitivity. So and it may also cause instability. So it's safer to use PI if you can accept some overshoot and undershoot.